Hello everyone, I am Dr. Madhurima Pandey. I am Assistant Professor in Physics at Holder Institute of Technology. Today I am going to talk about forced oscillations. So before you can see my lectures on simple harmonic motions as well as how the motion changed in the presence of damping that we have discussed earlier. So today it is a basically continuation slide. So today we will talk about forced oscillations. Now when the term is forced, that means the oscillation has been done forcefully. Okay. So yes. So this is the next slide, forced oscillations. So here you can see the basic definitions of a forced oscillations. But before that, I am giving you a very small example. When you talk about oscillation, that means the motion of a simple pendulum. Now, suppose you are considering that you have taken a pendulum in your study room and you make a disturbance of that pendulum. So what happens? Pendulum will oscillate, and after certain point of time, these oscillations will die out because of the presence of the damping or constants around its around the system, and which appears because of the presence of dust or air particle. So that is basically damped case. Now, if I ask you that no, you can't stop, or the motion of the pendulum cannot be stopped, it should be continued. So how we can get the continuous motions of oscillation? So that means we have to apply something externally, right? So that is basically called forced oscillations. So to make the oscillation in a continuous mode, what we have to do, we have to apply some external force or externally motions or external applications, that is forcefully. So that's how it names like forced oscillations. Okay. Now, so when we talk about any motions, any oscillations, first and foremost thing come to the picture, that is what will be the its equation of motion. So let us first consider here. We can see this is the one is the restoring force. Okay, you already know that restoring force is proportional to the displacement. Now, second one is the retarding force or resistive force, and it can be also named as damping force. So damping force, we know it is proportional to its velocity. So that is dy dt, the first order derivative of displacement. Now the usual, the inertial force, that is mass into accelerations. And in addition to that, there is an external force. Because of that, we get a continuous motions or continuous oscillation or forceful oscillations. That external force here indicated as F cos omega prime t. So now you can see here we take a nature of the force is periodic, because oscillation is basically a simple harmonic motion, and simple harmonic motion is basically periodic in nature. So whatever force you can apply externally, that should be periodic in nature. That's why we take cos omega prime t. Okay. So now the equation of motion, that this force, that is mass into acceleration, is basically this external force minus of this restoring force and the damping force. So now put all its values here, where k prime, these are basically, k is the restoring force constant, k prime is the damping force constant. Okay. So now take now only keep this first term on the right hand side and other terms in the left hand side, and then divide it by this m. So finally we can get this type of equation. So this is basically the equation of motions for forced oscillations. What is 2b? 2b is comes, this term 2b is comes here because of the presence of the damping. Okay, and omega square is basically the restoring force constant, which is basically k by m. Okay. So now to get the solutions of this oscillation, we have to deal with this equations 3.1. So let's go to that. Okay. So now two types of solutions we can obtain from these expressions. Okay. Why two types of solutions? So just keep that in mind, that in our system, we have two types of motions. One is the motions, natural motion, which is eventually dies out after a certain point of time, that is the presence of damping. And another is the motion comes from forcefully. Okay, so that means we have to deal with two types of motion. So that means there are two angular frequency. One is omega, another one is omega prime. What is omega? Omega is for natural frequency. natural frequency, frequency for the system. And omega prime is the angular frequency when we consider the external force. Okay, so you keep that in mind that we have to deal with two types of angular frequency. So that's why we get here two types of solutions. First one is the complementary functions. This complementary function is basically responsible for the its natural motions. That means the natural angular frequency. That's why. Okay, and this particular integral, you can see there is omega prime time appears, omega prime term appears. So that means this particular integral here comes for the motions which we obtain because of the presence of external force. Okay, so omega is its natural angular frequency, which is comes from its natural motion, which dies out eventually, and for that we get complementary function expression, one solution, and the second solution comes because of the presence of the external force. Okay. Okay. So now, so these are all the constants or all the definitions. Now here the important term is that steady state conditions. Okay. This is the steady state conditions. What is steady state condition? It is a very important one. Steady state condition that suppose if your system will oscillates with the same frequency as that of the external periodic force. Okay, your system, the frequency of this your system is same as the frequency of the external periodic force, then that condition is called steady state conditions. Okay, so now for the case of steady state condition, that means our frequency is omega prime. Omega prime is responsible for what? It is for external force. Okay, so this is our solutions. First we can consider depending on the steady state conditions. So now this is why. Now we take the first order derivative dy dt. When you take the first order derivative, the cosine term goes to sine and there should be minus term here. And then we again again take the derivative of dy dt. Okay, they differentiate it again with respect to t. Okay, so then we get d2y dt2. So this is all the basic differentiation. So now what we will do, we will put this d2y dt2 and dy dt in the parent expression. That means this 3.1. This expression, in this expression, we replace this d2y d2 and dy dt by that by this to differentiate term. So when you substitute those two values, these expressions look like this. Okay. Now you have to do certain simplifications or certain steps are there, mathematical steps. There is nothing important, nothing critical is there, only the simple mathematical steps. And finally, what we have to see that we have to compare on left hand side and right hand side. Which term we will compare? We will compare, you can see there is one term, cosine related term, and another, this is cosine omega prime t minus alpha, and there is another term which is from sine omega prime t minus alpha. So what we will do, we will compare the coefficient part of the cos omega prime t minus alpha for both sides. Okay, when you see, compare this coefficient term or compare with the cos omega prime t minus alpha term for both sides, we will get this first expressions. And again, when you compare the coefficients of the sine omega prime t minus alpha on both sides, left hand side, right hand side, you will get these expressions. And finally, after the calculations, the final result will obtain, that is the amplitude part. This is the amplitude part for the case of forced oscillations. And what also we can get, when you divide this two expression, we get the tan alpha, that means the phase term. So finally, the expression, the complete solution, that means the complementary function plus the partial integral, we get this 3.9 expression is the final expressions. Where this first term is basically comes from the natural motions, natural oscillations of the system, which eventually dies out because of the presence of damping. And the second term comes from the oscillation, which is appeared because of the presence of external force. Okay. So this we get the two solutions for the case of forced oscillation when we make a solutions for equation of motion. Now what will be the expression for energy for this forced oscillation? For that, we deal with the expression that is under the steady state conditions. Now put the value of A and alpha. Okay. So this is the A is amplitude, which we already obtained in our previous calculations, and alpha is this one. We already know. So So now what is the kinetic energy? Kinetic energy is the energy related to the motion of the system. The kinetic energy you all know that is half mv square. We can write the v as dy dt. So first take the derivative of y with respect to t, we get this one. Then we put that kinetic energy equals to half m dy dt square. Okay, just put the value dy dt square. Okay, and then in the next step put the value of a, amplitude. We take the square of the amplitude and write the value. Okay, so now we already discussed in the simple harmonic motion case that what is the, if we know the kinetic energy, then what will be the total energy? So total energy is basically maximum value of the kinetic energy that we have already discussed in the simple harmonic motion lecture. In the simple harmonic motion, we can prove that the maximum value of the kinetic energy is basically the total energy, or rather the maximum value of the potential energy is basically the total energy. And for the simple harmonic motion, the total energy is a constant. It can't change with, it can't change. Okay, so that means if we can calculate the maximum value of the kinetic energy, then we can get the total energy, right? So that we have done. Now, how we can get the maximum value? For that, we will focus on this sine term. Now, we all know that sine value, the maximum value of sine is +1. Okay, and the minimum is -1. So if we consider the maximum value of sine is 1, sine squared term is 1. If we replace this sine squared term as 1, then that means we get the maximum value. So that is basically we have done here. Then you can see here we don't put the sine squared term, we consider this sine squared maximum value is 1. So that means we get the maximum kinetic energy, and that is basically the total energy. So now here we have done some mathematical steps, and finally we obtained these expressions where this bracket, this omega by omega prime minus omega prime by omega, that we consider as a capital delta. Okay, we just define it. There is nothing special. We define it. This first bracket term is as a delta. Now here is an important thing. When we get delta 0, delta will be 0 when omega is omega prime. That means when the natural angular frequency of the system is exactly equal to the frequency for the external periodic force. That condition is called resonance conditions. So what is the resonance conditions? You can see the bold line. We will observe that when the frequency of the forcing system coincides with that of the natural frequency of the force system, the energy of vibrations of force system is maximum. Okay, so that means when your system natural frequency is exactly similar to the system frequency for the forced external periodic force, then we call that this is a resonance condition. And what is the beauty of the resonance condition? The resonance condition, all the term will give you the maximum value. If we consider energy resonance, then it will give at resonance, the energy will be maximum. Velocity resonance means at resonance, the velocity is maximum. Okay, so that means what will be then the energy value for the resonance condition? For that, omega should be omega prime equals to omega prime. And if we take omega equals to omega prime, then delta equals to 0. So if we put delta equals to 0, then finally this value we obtain, that is basically give you the value of energy, total energy at resonance. Okay. Now here you can see the sharpness of resonance. What is sharpness of resonance? For that, let us focus on this graph. This graph is basically the total energy versus this delta term. Now, when we get delta equals to 0, when omega equals to omega prime. And if you see that at delta equals to 0, the value of energy is maximum. Okay, we obtain the maximum value. Now, the question is that if our system is not in the resonance condition, so that means if omega is not equals to omega prime, so then what are the options? That omega can be greater than omega prime, which we have shown here, or omega can be less than omega prime. So in that case, what will be the nature of the total energy? It will be still at maximum or it will fall down. It will eventually fall down because the resonance condition does not appear here in this zone and in that zone. And that is basically called the sharpness of resonance. So what is sharpness of resonance? The sharpness of resonance is a measure of the rate of fall of energy of resonance with departure from equality between the frequencies. Right? So that means at delta equals to 0, there are the two frequencies have equal. So when the equality does not happen, that means when there is some inequality, when omega greater than omega prime or omega less than omega prime, that means in that case resonance condition does not appear. So in that case we have seen that the energy falls. Now in which rate it falls, that is basically giving you the sharpness of resonance. Okay, so that means here we have taken the ratio of the maxima energy and the total energy. Both are the things we have already derived in the last slides. Okay, and finally what we have done, we have just dropped this total term for our we drop the suffix term here, the total, and we write only E. Okay, so this is basically giving you what is the rate of fall of energy. Now this is the qualitative descriptions. Now let us take some quantitative descriptions, I mean some equations. So let us assume that at delta equals to delta 1, this E is half of E max. Okay, let us take that at delta equals to delta 1. Let us consider that E is half of the maximum energy. So that means just put that conditions here. If you put that E max by E should be equals to 2. And then if you do the further calculation, we get delta equals to plus minus 2V by omega. Now, what is the sharpness of resonance? S is basically denoted as, it is indicated sharpness of resonance. So this S is basically 1 by delta 1. So it is omega by 2B. So this expression is very important. That what is the sharpness of resonance? The definition of sharpness of resonance and as well as its equations or its value in numerical term. Okay. So these are the sharpness of resonance. Now next, what will be the value of amplitude at resonance? For that, what we have to calculate? This is the expressions of energy amplitude, already we know. So what we know that at resonance amplitude will be maximum. So to get this amplitude maxima, this denominator part should be minimum. So to get a maxima, this part should be minimum. Now how we can get the minima maxima? We know that we have to derive it. We have to take the first order derivative. Then we have to equal it to 0. Okay, so that only we have done. That we have take the derivative of this denominator term with respect to omega prime. And we make it equalize with 0. And if you do this calculation, do it in your home by hand. You can check that this omega prime is related to like this. This omega prime equals to root over omega square minus 2b square. This is called resonant frequency. Okay, so now the question is that what will be the value of amplitude at resonance? For that, what we will do, we will replace all this omega prime term by this root over omega square minus 2b square. If you replace this omega prime as a root over omega square minus 2b square, then you can check that the resonance value will obtain is this. This resonance values of amplitude will obtain like this. Okay, so this part is also important. Question may comes that how you derive the amplitude resonance and what is the expressions. So first you have to do the to get the maxima, we have to do the max minima conditions for the denominator, and then after that we get the value of omega prime and then just replace omega prime here, we will get the resonance value. Okay. Also we can get the power resonance, and these are the expressions can be obtained from power resonance. Okay, the derivation is not basically important, but what is the important part is here that how it varies with omega prime and what is the bandwidth. Okay, so that is the important part. So let us focus on this graph. So you can see this is the average power changes with the omega prime. Okay, and this is kind of a Gaussian curve we can obtain if you use these expressions. Okay, now here at the peak means this means it is giving the maxima value. Now when we get the maxima value, we already know that when we obtain the resonance conditions, that means when omega is equal to omega prime. Okay, so that means at when omega prime value is omega, we get the maxima value. Okay, so now let us consider that at two certain points omega 1 and omega 2, we get the maxima value of power maxima value is half. Okay, so these 2 points omega 1 and omega 2, these are called the half power points because at these frequencies when omega prime is equals to omega 1 and omega 2, we get the half of the maxima value of the power. So these 2 points are called half power points. Okay, so now So now at this point, that when this P average is half of its maximum value, the width of the curve at that point, the width of the curve, that means the distance between these two half power points, is called full width at half maxima, or commonly it known as bandwidth of the curve. Okay, so now to get the bandwidth of the curve, what we will do? What is its value? So that we have to do some small numerical steps. That is, first we consider that at the point of bandwidth, to determine the bandwidth, what we put, that P average equals to half of its maximum value. Okay, so then we know what is the P average value. So half of P average max equals to this P average value we put here. Left hand side, we replace the left hand side by these expressions. Then do some mathematical steps, and finally we get this omega square minus omega prime square equals to plus minus 2b omega prime. So from there we get this two solutions, one for omega 1, another for omega 2. So now if you solve it, then the bandwidth is basically omega 2 minus omega 1. And that is basically 2b. So how we get bandwidth to be omega 2 minus omega 1? That is basically when we take omega 2 minus omega 1, we get the width of the curve here. So that is basically bandwidth. So that we obtained as 2b. This expression is important. That what is the value of bandwidth? Now, quality factor. What is quality factor? Quality factor is basically the measure of the sharpness of resonance, which can be defined as the ratio of resonant frequency by the bandwidth. Okay, now the bandwidth is omega 2 minus omega 1. That can be also written as delta omega. So Q is basically omega, that is resonance frequency, by 2b. And exactly it is same as S. We have also obtained the same expression for S, that is sharpness of resonance. That's why we called the quality factor is a measure of sharpness of resonance. In this quality factor or sharpness of resonance, MCQ question may come or numerical question may come. Okay, I think it is clear. Now we make some analogy. What is analogy? So till now we know that how the mechanically oscillator, that means what is the simple pendulum, how we get the forced oscillation, that we have discussed. Now the question is that can we make any electrical circuit which can behave like a forced oscillation? For that, you can see we have taken a LCR circuit. There is resistance, inductance, capacitance, and it is attached with a alternating voltage. Okay, and that value of the voltage is given here. So that means if we use the Kirchhoff's voltage law, then what will be the Kirchhoff voltage law? That is the voltage across all the components, the summations of the voltage across of all the components will be equal to the voltage applied here. Okay, so that we have done. This is the voltage across inductance, this is the voltage across resistance, and this is the voltage across capacitance. Okay, now what we have to do here, we differentiate this expression with respect to t. Okay, so when you differentiate, this will be look like this. Now we consider this, if the voltage is alternating, then the current should also be alternating. So let us take I is I0 e to the power j omega prime t. Okay, so now what we will do? We will take di dt, d2 by dt2, and we replace all the values in here. Okay, so then we get these expressions. Then we make some simplifications here. Then finally we get I0 equals to V0 by this term. You can check it by your own. So now what will be the current I? Current I is I0 e to the power j omega prime t. Now I0 value we know. Now let us put this I0 value here. And finally we get V by Z. What is this Z? This Z is called impedance of the circuit. Okay, Z is called impedance of the circuit. This expression, how we can define this impedance? Impedance of the circuit, what does it mean? That what is resistance? That when a current passes through a circuit, then it suffers a constant. It suffers some disturbances. That is the resistance. Impedance is also some resistance, but this resistance comes from the summation effect of R as well as inductance and capacitance. All these three put a resistance, all these three put a constant, okay, all together. So that is called, so when the current passes through the circuit, it will suffer some disturbances or some resistances which can appear by this R, inductance and capacitance all together. So that is basically impedance. Okay. Now at resonance, that means when omega equals to omega prime, this part will be 0. So at resonance, then what will be Z? Z will be equals to R because this part will be 0 at resonance. So at resonance, LCR circuit is purely resistive because only the resistance part will be there, because at the resonance, this part will be 0. Okay. So that question also come that show that LCR circuit is purely resistive at resonance. So here you can easily prove that. Okay. So this is all about the forced oscillation. So today in this lecture, what we have learned that how can we get what the idea of the forced oscillation, its equation of motion, its solutions, the idea of the resonance, and we also here check that what is the value of energy resonance, what is the amplitude resonance, and after that we check what is the bandwidth, what is sharpness of resonance, and finally we make an analogy in between electrical circuit and mechanical circuit. So here is all the forced oscillations. I hope this lecture will help you for your further preparations. Thank you.